In this class, I would like to request about the Poisson distribution. A discrete random variable x is said to follow a Poisson distribution with parameter meter lambda if the PMF probability mass function of x is given by probability of x equal to r is nothing but e to the power minus lambda into lambda to the power r divided by r factorial. So where r is nothing but 0, 1, 2 and so on. So okay, and it is denoted by p of lambda. P of lambda means Poisson distribution with parameter lambda. Now here I want to say one thing. This Poisson distribution is a limiting case of binomial distribution. That means whatever problem we can solve using binomial distribution can be solved using Poisson distribution. Poisson distribution can be derived from binomial distribution under the certain conditions. So what are the conditions here I am to write? So Poisson distribution is a limiting case of binomial distribution. So how we can derive the Poisson distribution from the binomial distribution? Okay. So first condition is, under which condition we can think about the Poisson distribution, is first n, where n is the number of trial in case of binomial distribution. Here also n is the number of trial. So n, the number of trials, are infinitely large. That is, n tends to infinity. Remember that infinitely large means it is not infinity. It is, however it large, still it can be countable. Okay. And the second condition, that means if the number of trials are more, then instead of binomial distribution we can think about the Poisson distribution. And the second condition is P, the probability of success. The probability of success in each trial is very small. That is, P tends to 0. Okay. Obviously, if the number of trials are more, then probability of getting a successful event is very less. So it corresponds to, means this is the consequence of the first one. If the number of trials are more, the corresponding probability should be very small. Okay. And the third condition 3 is n into p, which is lambda. So n into p in case of binomial distribution is the mean. In case of Poisson also, n into p equal to lambda. So lambda will be the mean of the Poisson distribution, we will derive it hereafter. Okay, so np equal to lambda must be finite. It should not be infinite. It should be finite. Okay, it should be finite. Or from here we can have n equal to, or you can have p equal to lambda by n, or q equal to 1 minus lambda by n. So we can have this one. So under these three conditions, we can derive a Poisson distribution from the binomial distribution. So here I am not giving the detail of the binomial derivation. Just I will go for the MGF of binomial distribution. MGF for binomial distribution. How can we find the moment generating for the normal distribution? So MGF of Poisson distribution. Poisson distribution. Moment generating function of Poisson distribution. Since this Poisson distribution is also for the discrete random variable, therefore m of t, moment generating function, we can write here summation r equal to 0 to n, or infinity we can say, e to the power tr into pr. But here pr is nothing but this. Pr is nothing but e to the power minus lambda into lambda to the power r divided by r factorial. And so we can have here this is equal to summation r equal to 0 to infinity and e to the power tr into e to the power minus lambda, lambda to the power r divided by r factorial. And so we can put e to the power lambda outside, which is independent of r, and we can write r equal to 0 to infinity. And since it is e to the power t to the power r is there, and it is lambda to the power r, so e to the power t whole to the power r into lambda to the power r divided by r factorial. And so I can combine these two terms and I can put them together. So e to the power minus lambda summation r equal to 0 to infinity, and we can have lambda e to the power t to the power r divided by r factorial. Now here I want to say one thing. You know the formula of summation x to the power n divided by n factorial. N is from 0 to infinity. So this is nothing but 1 plus x by 1 factorial plus x square by 2 factorial and so on. So, and this is equivalent to e to the power x. Now it is this in that way only. In place of n I am having r. So if in place of x I am having lambda e to the power t. So if I can compare these two, this can be written in this way. So m of t will be nothing but e to the power minus lambda into e to the power lambda e to the power t. So this will be my moment generating function. This will be my moment generating function. Now using this moment generating function, we can find mean and variance. Mean and variance of p lambda. Mean and variance of p lambda. Poisson distribution. Mean and variance of Poisson distribution. So how can we find mean and variance of this? From the moment generative function, we know that mean mean equal to m dash of t and then put t equal to 0. So now we will find a derivative of this one with respect to t, and after that we will put t equal to 0. So e to the power minus lambda is constant because it is independent of t, then there it is equivalent to d by dt of e to the power at. A is nothing but lambda, and in place of t I am having e to the power t. So what is the derivative? That is a into e to the power at. In the similar way I can have e to the power lambda into e to the power t, e to the power, so this is a into e to the power at. So e to the power at into e to the power lambda et into a. A means lambda e to the power t. What is the derivative of that one again? Lambda into e to the power t. And then put t equal to 0. Then put t equal to 0. If I put t equal to 0, we'll get e to the power minus lambda, and this e to the power t equal to 0 is 1 into lambda into e to the power lambda, and so I will get it lambda. I will get it lambda. Similarly, if I want to find expectation, so mean is nothing but expectation of x. Similarly, we can find expectation of x square. That will be nothing but m double dash of t. After that, we can put t equal to 0. So if you find that and we will put the value t equal to 0, then we will get lambda into 1 plus lambda. Lambda into 1 plus lambda. And so variance of x will be nothing but e of x square minus e of x whole square. And so that will give you lambda plus lambda square minus lambda square. And so we will have lambda. So remember, in case of Poisson distribution, mean equal to variance. So we can have mean equal to variance. Both are lambda. But lambda is nothing but number of trial into p. Lambda is nothing but number of trial into p. So this is the moment of the random Poisson variate, the random variable which follows Poisson distribution. Now here I want to give you the central recurrence formula for central moment. So here I want to give recurrence formula for central moment of P lambda. P lambda means Poisson distribution. So what I will do here is actually formula is we know the central moment. We know the central moment is mu k, and that is nothing but e of x minus e of x to the power k. This is the central moment. Okay, and so here x is my r, so I can have this is equal to, I can write this one is equal to summation r equal to 0 to infinity r minus e to the power x is nothing but lambda to the power k into pr. Pr is nothing but e to the power minus lambda into lambda to the power r divided by r factorial. Now we can differentiate one, and if you simplify, differentiate one with respect to lambda, and simplifying we get what we get if we differentiate that one and if we simplify it, d mu k by d lambda, d mu k by d lambda will be nothing but minus k mu k minus 1 plus 1 by lambda mu k plus 1. And from here, what we will find, mu k plus 1 will be lambda into d mu k by d lambda plus k into mu k minus 1. So what is the meaning of this? So if you know the previous two values, then we can find the next value. Here we remember that here mu 0 will be always 1. Mu 0 will be always 1 and mu 1 will be equal to 0. Mu 1 will be equal to 0. And using that, we can able to calculate mu 2 because mu 0, mu 1 we know, so we can go for mu 2, mu 3, mu 4. So now I will tell here what will be for k equal to 1. K equal to 1, I will have mu 2. Mu 2 will be nothing but lambda into d mu k equal to 1, I'm putting d mu 1 divided by d lambda k equal to 1 into mu k minus 1 is nothing but mu 0 into mu 0. But mu 1 is 1, derivative of 1 with respect to lambda will be 0. Mu 1 is 0, so this is with 0. Mu 0 is 1, so it is 1. And so if you simplify it, we will get, so this is called fast moment. Similarly, for k equal to 2, we will get mu 3. Mu 3 will be lambda into d mu 2 divided by d lambda, d mu 2 divided by mu lambda plus 2 into mu 1. 2 into mu 1. So if you simplify, mu 2 is equal to lambda, d lambda by d lambda is 1, mu 1 is 0, and so finally what you will get? You will get here lambda. So for k equal to 2 is also lambda. Similarly, you can go for k equal to, for k equal to 3. K equal to 3 will be mu 4 is equal to lambda d mu 3 divided by d lambda plus 3 into mu 2. 3 into mu 2. And so finally what will get? Lambda into mu 3 is lambda, so it will be 1, and it mu 3 into mu 2 is also lambda, so 3 lambda. Okay, so like that we can able to find the recurrence relation for the central moment of a Poisson variate X.